Okay, so today we'll be talking about quite an interesting topic and quite an advanced topic, I would say. But I'll give an overview of neural architecture search. And that's, again, one of the other methods of neural network optimizations to have more efficient implementation on hardware. So this is, again, something that won't really dive into hardware or systems, but we're still kind of at that neural network level. How do we make the neural network itself more efficient? So we looked at quantization, pruning, knowledge distillation, and now neural architecture search. I should say NAS or neural architecture search is usually kind of under this AutoML umbrella or automated machine learning. And that includes more than NAS. It's like neural architecture search, hyperparameter optimization, and something called meta learning. But we will focus on neural architecture search specifically. So how many people already kind of know what that is, just kind of by definition? 1, 2, 3. So a few people. Okay. It's always good to gauge. So the motivation here is that people have been designing neural networks to do a specific function. So AlexNet has this very specific topology. It has 5 convolutional layers, 3 fully connected layers. There was a lot of intuition going into it from classical image recognition work. And so they said, we need a bunch of features. The deeper we get into the network, the deeper the layers should be, the finer grained the features will be, and the more of them that we will have. So we will select kind of, let's select, the depth of 384 here, number of filters. So who thinks, this 384 number is the right number to use here? Right, it's as arbitrary as choosing any other number, frankly. And then, people continue to do that for a long time. So I'm showing here VGG, which is also kind of a manually designed neural network that outperforms AlexNet. And again, it was based on a lot of intuition, that convolutional layers are much more important than fully connected layers. And they're also computationally less expensive. So let's add more of those, right? And they also found out that, stacking multiple convolutions with a small filter size, so 3 by 3 convolutions were the main thing in VGG, were enough. We didn't have to go all the way to 7 by 7 convolutions and 5 by 5 convolutions, which were present in AlexNet. And then someone thought about it a bit harder. In fact, not someone, but like a huge team of people at Google kept thinking about how do we make this more efficient? And they came up with MobileNet. Before that, at Microsoft, people thought about how to make gradients flow better, and they came up with ResNet. But the key thing here is that, and this is kind of one of the superpowers of neural networks, is that many topologies and many network architectures can perform the same function. The training algorithm, like SGD or something, is very powerful. It can actually train parameters in a parameterized neural network of any architecture or any topology. And so the question becomes, how do we design the best one that gets the best accuracy? And that's what neural architecture search is all about. So yeah, how do we manually decide on these operations? It's all intuition-based and kind of trial and error. So instead, we'll show something that's more automated. And so that's kind of the movement behind neural architecture search. And there is a lot of industry interest in this because it automates a problem that has no right answer, really. And so we're going from manual design, which is, as I said, based on a lot of intuition, has a lot of manual trial and error, and takes up a lot of human time. And as we saw, kind of the biggest cost for companies is actually the human time now, like the software developers and the people doing the work. Going to automated design. So it's still trial and error, as we will see in many cases. It's very intelligent and automated trial and error. It doesn't require human time. It requires GPU time, which is arguably also very expensive. But people are looking into how to make that also run a lot faster. So what is it? What is this neural architecture search, right? In its simplest form, it's quite simple. You have kind of some algorithm that proposes a deep neural network. So it proposes its green one here, and then we want to know how well this proposal works. So we train this green neural network and we get some accuracy. In this case, it's 79%. And so what we do next is, we change that neural network a bit by changing the number of layers, the filter sizes, the number of channels, the type of operation or anything. And then we try it again. So we train that new orange colored or yellow colored neural network, and we get a different accuracy. And so if we keep doing that repeatedly, then we will eventually basically have a bunch of neural networks that we tried, and we can choose the one with the highest accuracy, right? So what I just described is called random search. You're just randomly changing the neural network architecture. We are evaluating it in terms of accuracy, and we keep the best one. So this is the most naive kind of search, but it actually works. It works quite well, and it outperforms a human design because you have this thing that's automated, that's trying a bunch of neural networks. So we will not just talk about random search. In fact, we won't talk about it again except to compare it to other algorithms. But there are many other much more intelligent algorithms people have been using here. NAS kind of started with reinforcement learning, and so we will talk about that first, but then quickly moved to more genetic and evolutionary algorithms. Then there are very modern algorithms that people use that achieve a very good sample efficiency, or basically we try very few neural networks before we get to a very high accuracy one. And so we'll talk about prediction-based search and differentiable architecture search. Finally, on this side, this box here actually takes a lot of time. So some neural networks, will take days, weeks, months, years, GPU years to train. And so how do we actually do this in a scalable way? And so we'll talk about a few ways to make that faster, something called parameter sharing, which is not written here. And we will also talk about proxies that have kind of a reduced form of training instead of doing the complete training to kind of evaluate model accuracy. Then we'll also talk about the objective. So in this picture, I'm showing that the objective is accuracy. Can people think of what other objectives we can have here? Latency, yeah, so that's correct. So we can actually optimize the neural network for more than one thing. In the classical neural architecture search, we're just trying to optimize accuracy and get to the best performance of the neural network. But we also care about other things, like how fast it runs on a mobile phone, for example. And so let's start with kind of the reinforcement learning classical work. Yeah, number of parameters would be a possible objective. And this is what I would call kind of a proxy for latency or runtime on a phone or on a GPU, because generally the larger the model, the longer time it will take. But that's not a hard rule, as we will see as well. Okay, so again, by show of hands, who kind of knows what reinforcement learning is? Okay, that's good. So many people know what that is. So I don't need to talk a lot about this. But basically, the process of optimizing a neural network parameters with reinforcement learning was first kind of proposed by people from Google. And the idea here is that our searching algorithm is kind of replaced by deep reinforcement learning in this case. So what do we do here? We basically use a policy gradient algorithm in which, the way that works is that we have a function parameterized with some parameters, let's call them theta. And that function in deep RL is usually a neural network. And so we can, in this case, we have a recurrent neural network. And in every time step, we're basically trying to predict what the best value for these parameters are. So choosing the number of filters, and then choosing filter height and filter width, stride height, and so on for each operation in the neural network. And the way they do it is that they actually use like a recurrent CNN here, and they do a categorical classification here. So they have a softmax output, and they choose one of different discrete values for a number of, for each of those hyperparameters of a neural network. And so the action here would be kind of to choose the value for one of those architecture parameters. The state space is what we will call a search space. And this is the set of all possible deep neural networks in the search space given the parameters that we provide. And finally, for reinforcement learning, the way you give feedback to your algorithm is you provide some reward value. So what would be the reward value here? What feedback would we get from a neural network that we try out? Any guesses? So we want to kind of have a value that quantifies how good this neural network is, right? So am I? Yep. Yeah, that's correct. And what were you going to say as well? Yeah. Yeah. So you're both correct. So basically, you know, in our very simple case, it's just accuracy, right? So we try a neural network with specific values for those, you know, hyperparameters, and then we get accuracy. We feed it back to the controller. It updates the parameters of our deep, you know, neural network controller, and then it tries to choose or modify the next neural network that it proposes so that it works better. So this is just, you know, again, in our random search example, we were randomly changing the neural network. We were randomly trying another one and then measuring its accuracy and keeping the best one. In this case, we have some feedback, and that feedback is in a form of this reward here that allows us to kind of quantify how well this trial worked. And so we give feedback to the controller that will update its policy so that the next time it proposes a neural network, it takes that into account, right? And so I briefly mentioned the term search space while I was talking here. And in the previous picture, we had you know, all of this filter width, filter height, and specific hyperparameters. But here I'm showing a very simple search space. And what that is basically just, you know, we have 7 layers in a neural network, and we have 4 choices for the operation of each layer with specific hyperparameters, right? So yeah, so we get to choose at each layer which operation we put there. And so can someone tell me what the size of the number of possible deep neural networks for this simple search space would be? So, come on. 4 to the power of 7. So that's correct. So if at every layer we have 4 choices and we have 7 of those layers, then, you know, it's exponential with the number of layers, right? So. So that's a good question. So the question is whether there are heuristics to, you know, eliminate nonsensical models or invalid models. And typically, from what I've seen, no. So some models can even be invalid completely, and that's when we have more complex topologies and we have some skip connections and 0 operations, so like no operation. You can have a model that has everything is no op, right? And that's an invalid model. You quickly kind of weed out those models when you put them through an evaluator, because you start to train them and they get kind of 0 accuracy consistently, or they error out or something, and you catch the error and you say, okay, move on to the next model. But I haven't seen kind of manually crafted heuristics to guide neural architecture search in a specific way. So if you look at all of these neural networks before you make a decision, then that would be exhaustive search. And of course, I mean, that would be ideal, but you wouldn't do that because you don't have enough GPUs, basically. And so that's why you need an intelligent search algorithm to kind of navigate that search space and hone in on the best path to take, or the best changes to do to the neural network to lead you know, to a high accuracy one in this case. So I mean, I've seen for search spaces of, for example, 32K or even 100K, 100,000 neural network example, like neural network possibilities. I've seen search algorithms converge to a good value in about 100 to 500 search trials. So that's approximately kind of the fraction there. So yeah, you search very little of that space, but you try to find the best model in that case. And you don't have to find the best model, right? So you're trying to find a model that kind of meets your QoS or quality of service constraints. So something like, I need at the minimum this accuracy or this latency. That's enough. Oh yeah. Yeah, exactly. You're not shooting for the global maximum here. So, um, so as I briefly kind of said before, for the reinforcement learning case, this turns into a classification problem. So, for each choice that we have to make, we have this kind of discrete set of classes, let's call them, and we basically put our RNN output through a softmax classifier to select which one to choose. And so the feedback would then guide your RNN parameters to choose a better one in the next trial, and so on. Okay, and so when people tried this, they found that it outperforms all human-designed networks easily, and of course it's not so easy because in this case, you need to spend a lot of GPU time to actually get to those results. So can someone guess how many GPUs we need to kind of do this? Just a number. So this is the first paper on neural architecture search, and the hint is that it's by Google. So can you guess the number of GPUs, order of magnitude? Thousands. Okay, a bit lower actually. So 500. Yeah, we're binary searching now. So it's so they actually needed. Oh, it's not in this slide, but they actually needed 800 GPUs to get this result, right? And so so that's a lot of GPUs for a, what is this, 1% accuracy improvement, and then more GPUs to get to this one. But basically it's a lot of compute power. And we talked before about how training one neural network could use hundreds of GPUs for a long time. And here it's even if a neural network trains really quickly, we need to do so many trials before we get to the right answer, or a good enough answer that beats kind of manually designed networks, that it's people are questioning the scalability of this approach, and they're also questioning whether people other than Google can run this, right, or Amazon or Facebook. And so one of the main areas of research here was how to find a better search algorithm, a more efficient search algorithm, right? So we want to reduce the number of trials and thereby reduce the number of GPUs that we're using. And so the next thing people tried here were genetic or evolutionary algorithms. And there are many variations of this, but I'll describe one of the very successful ones called aging evolution. And so so what we do here is, we initialize something called an evolution pool with a bunch of neural networks. In this case, we have 8, right? And we initialize that typically randomly. And each one has an associated accuracy with it. What happens in aging evolution is that we take the best model and we mutate it. So we do some change to it and come up with a new model. And then we take the oldest model in the evolution pool and we remove it. So that's why it's called aging evolution. Basically, the oldest one dies. Whether it has really good accuracy or bad accuracy, that's not a factor. It's just it has been in the evolution pool for a long time. And then finally, we put the new model, the new mutated model, the child model, into the evolution pool. And we repeat this again and again and again. And so, as you'll see here, we no longer have an RNN controller, and we no longer have parameters that we're updating. This is just kind of a directed search algorithm, essentially. And there are so many search algorithms out there that we can use to do this as well. But this one has been quite successful. And in general, genetic and evolutionary search algorithms have been very successful as optimization algorithms, so as discrete optimization algorithms. And so that's what we do. We initialize the evolution pool. We repeat it n rounds where we do, we mutate the best model, remove the oldest model, and we keep doing that again and again. So that's a good question. Why do we remove the oldest instead of the lowest accuracy? So in all of the very good search algorithms that navigate large search spaces, you have a good balance between something called exploration and exploitation, right? And so by removing the oldest one, you're increasing the exploration of this algorithm. Even if it's the best one, you want the algorithm to explore new areas of the search space that haven't been explored before. And so let's say we always remove the lowest accuracy one. That might mean that we're always evolving the same one again and again and again. So it's kind of going, let's see, what would be the example? It's going like along one tree in the evolution space, as opposed to kind of exploring in different directions. So yeah, so that's kind of the main reason there. You want to have a bit of exploration, not just following the best path in the search space. So, I mean, there are so many variations actually of genetic and evolutionary algorithms, and some of them may have a different heuristic for pool eviction and selecting which one for mutation. So here, you know, it selects the best genotype for a mutation, and that's a very greedy thing. Like you just, you know, find the best one, make it a bit better. Some of them would randomly select one for mutation, for example, and always remove the worst one. So there are many heuristics there. I only present this one because it was introduced in the context of neural architecture search, and it works quite well. But you can think of many heuristics for sure. So, okay, and then, you know, when I started reading those papers, I was wondering, you know, why did we even use reinforcement learning in the first place? Because actually, most of the experiments I ran and most of the literature now agrees that RL doesn't actually work that well with neural architecture search. It's just it's so hard to tune. Usually, you know, there's something called reward function engineering. There's just so many hyperparameters for RL for it to converge quickly on a good model. And so, why did we use it in the first place? And why you know, did the first paper actually use RL? And I will say that it's just arbitrary. So people at Google really liked reinforcement learning at that point, and that's why they used it. That's my opinion. But I would say currently evolutionary algorithms are among the best kind of sample-based search algorithms out there. And so, so this is from the same evolution paper written down there. And so basically, when they did a bunch of random trials with, you know, RL, with random search, and with evolution, they found that, you know, approximately evolution was always kind of better, or mostly, in most cases, led to a better result. And this was verified in later works as well. And so this is here a plot that you will see a lot in neural architecture search papers. And, you know, on the x-axis is how many trials we did, or what is the number of hours that we're using for this experiment. And on the y-axis is, you know, the best accuracy achieved so far. So, so yeah, this is the curve that, you know, a NAS person really cares about and tries to basically make better. And dominating existing approaches means, you know, you're higher in the accuracy part and you're lower in the experiment time part. So anything here would be better, basically. So, I mean, a good question now, if I'm sitting where you are, is why are we even talking about this? So far we just, you know, we're optimizing for accuracy. And so what does that have to do with systems? We care about, you know, hardware efficiency, designing hardware, scaling problems to multiple hardware nodes, and all of this stuff. So the answer is basically what we'll talk about next. So there's a lot of intersection between neural architecture search and efficiency. And the first and very obvious one is what people already pointed out, is, you know, hardware-aware neural architecture search. Instead of just optimizing for accuracy, I also want to optimize for latency or power consumption or something that, you know, is related to the hardware itself. Even if I lose some accuracy, maybe I want to fit a model to a mobile phone, and I don't mind some accuracy loss just to make it work, because otherwise it doesn't even work. And so we will talk about this hardware-aware neural architecture search, where we optimize both accuracy and something else. And then the second, more kind of subtle point is the scalability of NAS. So while we won't talk about specific hardware systems to scale NAS, we will talk about different approaches that people have successfully used to shrink those, you know, 800 GPUs down to a few minutes in some cases, actually. And so people have really kind of optimized search algorithms and aspects of the search algorithm to this specific problem of neural architecture search because of its importance. And so, so we'll kind of answer the question of how can we run NAS if we don't have hundreds of GPUs. We'll actually start with the second one. I don't know why I said this is 1 and this is 2. Yeah, but we'll start with the scalability of NAS first. Okay, so far this is kind of what it looks like. You have hundreds of servers, and we're running neural architecture search on each one, and we kind of have kind of one of the servers synchronize the result and update a controller or update the search algorithm and so on. And people have thought about how to implement those algorithms in parallel as well. And as I said, this first NAS paper used 800 GPUs for 28 days. And so, 800 GPU months, basically. And so that's just for this 1 or 2% accuracy improvement. I mean, 2% is still significant in these kinds of problems, but it costs a lot of money and power here. And so to get more efficient neural architecture search, there are typically kind of 3 things that we can start to think about and start to optimize. We already talked a bit about more efficient search algorithms. So basically in this sample-based neural architecture search, how can we reduce the number of samples? So the number of trials of a neural network before we find a really good one. So that's the first thing. The second thing is, these very large search spaces, as someone already asked, can we shrink them? Can we use smaller search spaces? Can we search for something that's really important instead of searching for the whole thing and leaving it open-ended? And the final thing is, instead of fully training a neural network, can we do something else to evaluate how good that neural network is? And so here we will look at, inexpensive proxies where we basically reduce the amount of training to get an indication of the ranking of different neural networks. And so we'll talk about search space first. And the typical thing that people have been doing there is something called cell-based NAS. So you'll see it being called cell-based NAS or microcell NAS or microsearch or something like that in the literature. And basically the big idea here is that you have a neural network architecture, and this is what we call a DNN skeleton. So the skeleton is fixed. This is what it's going to look like, right? But then there is this cell here. There is this cell here, which you don't know what you want to put in this cell, and that's what you're searching for. But once you find the architecture of this small cell, you repeat it n times in this stage, and then you repeat it again n times and n times here. So instead of searching for all the operations in the entire neural network, you're actually searching for just operations within that one cell. And what does that cell typically look like? In this example search space, it looks like something like this. So it has some flexibility in the interconnection between layers. It has different operations that it can choose along each layer. And so you can choose a number of different cells. So the search space size here is the size of the search space of this small cell instead of being the size of the search space of the large model. And so if this is typically called microsearch in the literature, the opposite of it would be macrosearch, or that's when you search for everything in the neural network. And typically what that means is you still have a skeleton, but each one of those cells can be different, right? So in micro cell or cell-based, all the cells are identical. And in macro, the cells can be different. And so obviously there's a huge difference in the size of the search space when the cell can be the same or different. And so for this example, if we have 10 cells, 5 operations per cell, and each operation has 3 choices, can someone come up with, the search space size? So I'm saying the number of choices here, but what is the search space size for micro and macro search? We can start with microsearch because it's actually simpler. So you just multiply. Okay, so it's 3 to the power of 5, right? So in micro search space, you have 5 stages, and as we did it before for the other one, which had 7 stages and 4 operations, here we have 5 operations and 3 choices for each one. So it's 3 to the power of 5. But now, what if it's a macro search space? what happens now. So now each cell can also be different. 3 to the power of 50, not quite, but you're shooting in the correct general area. So, okay, I'll click. So basically, oh, 8 choices. I read the 8 as 3. Maybe that's what confused everyone. Sorry. I told you I can't hear and I can't see really well. So I'm actually joking. So yeah. So for wait. It's 3 here and it's 8 here. Who would do this? Like, it's very odd. That's what happens when you kind of create slides, after midnight. So, okay. So if we have 8, let's go with 8. If you have 8 choices per layer, or 8 choices for each operation, and you have 5 operations, then it's 8 to the power of 5. And that's, 32,000 models. That's actually not too bad, right? But in a macro search space, if you have 10 of those cells that you're repeating, and you're not repeating an identical cell anymore, but you're choosing the architecture of each cell, it becomes a huge search space, right? Like it's 8 to the power of 5 to the power of 10. Actually, yeah, I think that's right. So in this case, it's 10 to the power of 45. So it's a much larger search space. And that's why it's way easier to actually search for kind of a specific cell architecture and repeat it in a predefined skeleton than searching for everything, than making everything variable. And the intuition there has been always that, most of the neural networks that actually work have a specific block that's repeated again and again, with some scaling between different stages, but it's the case for, ResNet, for MobileNet, for EfficientNet, for all of kind of the state-of-the-art networks. And so it works fairly well. Yeah, so that's a good question. So is macro search searching for the skeleton or search for every cell? So typically what it means is that, you have these cells here that are repeated throughout the network. What it means is that each cell can be different. So that's what macro search usually refers to. Whereas micro search, all of the cells are the same. You just search for one and you stamp it out in your model. Yeah, so that's a good question. What's the criteria for stopping the evaluation? So typically, you have your own constraints, application-driven constraints. So you want it to run within 5 milliseconds, or you want it to have at least 80% accuracy, or you want to beat your manually designed network, for example, or the existing network. And once you find something reasonable, you stop. So that's basically it. So that's a good question. In practice, are the results for macro better than micro? So in practice, I haven't seen macro search used a lot, actually. So in most industrial cases, at least that I've worked on and that colleagues have worked on, they're doing micro search. And you'll find that at least 80% of the literature is on micro search. But those few papers that look at macro search, they start by saying, the larger diversity in models can get us better accuracy. And that's why we want to look into those more complex search algorithms. And so typically, I would expect macro search to have a model with better accuracy in the search space. So that's an assertion. So that's what I would expect. But in practice, people don't go there because it's just so hard. But there are some emerging algorithms looking at that now. So that's also a good question. So the predefined skeleton is basically manually designed. So again, people follow their intuition. They want deeper layers to go later. They want some max pooling after each layer or something. And so they just define the skeleton manually to get some, also by using trial and error. Or they borrow it from a manually designed network. Okay. Okay, so we talked about search space size and cell-based design. Now let's talk about another technique which has also been very successful in making NAS faster. And so that's called parameter sharing. So it's from this paper cited here. And basically the idea here is that when we propose a deep neural network, we have to train it. So I'll color it green when something is trained in this case, or something other than gray. So I've already trained kind of a 3x3 convolution in the first stage, and a 5x5 convolution in the second stage, and a 3x3 convolution in the third stage. So now when I propose another model, I'm actually using the same middle layer here. So I'm using a 5x5 convolution in the middle, and I already trained this before. So what parameter sharing does is that instead of initializing everything to scratch again or randomly and training everything from scratch, I'm actually borrowing the parameters that I've used before or that I've trained before in a model. And so when I now train this new proposal here or this new neural network, I only train those two extra ones that I'm coloring in yellow. And the third one, I just borrow the parameters that I've trained before. And then when I propose another neural network, I do the same thing again. So for example, here, I've already trained a 7x7 convolution in the first stage. I've already trained a 3x3 convolution in the last stage. Even if they're two different training trials, I just borrow the parameters, and then I only need to train the model in the middle, right? And the intuition here comes from transfer learning, where you can always train a network and then change the last few layers and specialize it for a specific task. And then what it hinges on is whether this actually works, and people have found that it works empirically quite well. And obviously you shrink your training time by a lot, because once you train one of your choices, it kind of reduces a large number of possible trainings in your search space. So this is where it kind of starts. We start customizing new search algorithms specifically for neural architecture search, right? So this is something very specific to neural networks. So if I can't really apply this to a search algorithm that's just optimizing something else that has no parameters and has no notion of layers. So this is where people are taking current search algorithms, which if they're RL or genetic algorithms or something else, these are just generic optimization algorithms, right? But now with parameter sharing, we're actually focusing on the specific domain of neural networks. And in this specific paper, what people have found or people have measured is that it's 1,000 times faster than conventional neural architecture search without parameter sharing. Okay, so on to kind of another related thing, which is training proxies. So instead of taking each one of our trials and training it to conversions, we can actually just do something else. We can train it for a fewer number of epochs, or we can subsample the training data set, or we can use lower data resolution. Basically, we can do a bunch of things to speed up training. The final value will not correspond to the value that we care about, which is the performance of that model on the task that we're training it for. So for example, ImageNet classification. But we at least will get an indication of how good the model is. And again, people have found that halfway through training, for example, you can already tell whether one model is better than the other. And so in this case, compared to full training, if we have 5 trials or we're trying 5 neural networks here, with a proxy, for example, if we have the number of epochs, we can either half our runtime or we can double the number of trials, right? And so these are called, generically reduced training proxies. And they're also kind of standard now in neural architecture search. No one does full training except for that very first Google paper, I think. And so a question now becomes, what is the expected speed up for a proxy that uses, half the number of epochs, half the training sets, half the data resolution, and half the number of channels? And I mean, think about it for a minute or something. But the speed up is quite surprising. It's a very large speed up, right? Any guesses, Aman? 16? Okay, you're close. I think I'm right. So it's I think it's 32 because when you reduce the number of channels, I think it has a quadratic effect on runtime in your stem convolution. But yeah, so you know, just by doing these reductions, you can get up to 32 times faster, and that's, you know, that's a huge speed up. That means you can try 32 more times, more models. Yep. No, so no, they're all 0.5, but the last one with the number of channels, I think it has a quadratic effect on runtime when you're training a model. Maybe it's because of the forward and backward pass, but yeah, so I can do it with pen and paper later, but I think it's quadratic. Yeah. So yeah, so we looked at those proxies now, and the fact that, you know, we don't have to actually do full training. And so people actually use these things in conjunction. They kind of do parameter sharing and they do reduced training proxies. So they basically, all of these different optimizations are stackable. You can use a bunch of them at once. We also said that, you know, another way to speed up NAS is to choose a better or more intelligent search algorithm. And this is one of the things that we worked on back at Samsung is, you know, we found a key observation is that you don't actually need to know the exact accuracy to evaluate whether a model is good or bad, right? You just want to know relative to another model, so between A and B, which one is better. So we trained this, you know, meta model called a binary relation predictor. Basically, it's a neural network which takes as input two model architectures and predicts which one is better. And so, you know, you train this predictor on T, D, and N. So you take, you know, T of those, and you train the predictor to correctly identify which one is better based on the architecture. And then we use the predictor to sort the rest of the models based on that. So it's, I mean, it's not exact. It won't always give you the right answer. But then once we do this iteratively, we can actually have a predictor that when you input any two neural networks in the search space, it kind of tells you which one is better. So this is supervised learning, right? Because in this first step, we train the predictor on T examples where we know which one is better. We train them to completion. And so again, this is the plot that we always care about. You know, you have runtime on the x-axis and accuracy on the y-axis. So we already saw, you know, random search. And you know, we actually can see that reinforcement learning here is close to random search in this data set. And that, frankly, that was my experience with a lot of this. Maybe we're unable to tune RL well for each search space, but it has so many hyperparameters, it usually performs very poorly when you adapt it to a new data set. And then aging evolution is quite good. So, you know, it's definitely much better than random search and reinforcement learning. And then here's the curve for our binary relation predictor NAS, where it's even better. And, you know, converges to a very good model really quickly. And so, I mean, a final note about this is that there are actually so many search algorithms now, a lot of them based on these surrogate models or these predictors, and a lot of them based on other things like Monte Carlo search or other kinds of searches. And so this is kind of a long topic with a lot of papers, but this is one example of this. So far we kind of talked about, you know, the scalability of NAS from you know, 800 GPU months to something much better. And we talked about, you know, how to, you know, shrink the search space size to use the cell-based search space, which gets you very close to a really good model. We talked about, you know, parameter sharing, and we talked about, you know, new search algorithms. And finally, we talked about, you know, reduced training proxies as well for shrinking the evaluation time. So one more thing before we talk about, you know, hardware-aware neural architecture search is this notion of a SuperNet, and beyond that, we'll talk about differentiable architecture search as well, really quickly. So basically, what I'm showing here is, you know, we can construct this network. If you think about it, we can construct a network or a cell in this case that has all possible choices. right? And so if I said, in each one of those edges, I can choose either a conv 3x3, 7x7, or average pool, I can actually build a neural network with all of these choices, right? And so that's what people typically refer to as a SuperNet, which is a superset of all of the possible networks in my search space. And so how do we do that? It depends on the work, but in the most common case, what we do is we actually add the output of all of these layers. And so then we can construct a fully end-to-end trainable SuperNet with all of the candidate operations in that super network. So, I mean, in this diagram here, I just have an addition here, but usually, so they call this a mixed operation or a mixed op. Usually it's actually a softmax of all of the output that we use here to actually, this is premature. Let's just say, yeah, we add all of the outputs here of the different candidate operations, right? And so, so the question now becomes, what do I do with this SuperNet? And that's where, differentiable architecture search comes in. We add something called the scaling parameters or architecture parameters on each edge. And so let's call them alpha 1, alpha 2, alpha 3. And this is, let's say this is the importance of each of those operations. So, and then when I train a neural network, I can actually make those alpha values, those architecture parameters, trainable as well. And whichever, is trained to be a very high value, that means it's more important. And whichever has a lower value, it means it's less important. And that's how I can select, my operations here. And so that's probably not clear yet. So let's take a look at it again. So basically, I have this cell. I want to search for what operation to put on each of those edges. I construct a SuperNet with all of the operations combined with this addition and these alpha values as well. And then while I'm training the neural network, I'm also training those architecture parameters, right? So I'm also training the value of those alphas. And as I'm training the neural network, some of those alphas will be, smaller and smaller, and so they don't really contribute to my output anymore. And some of them will be, larger. And that's why we use a softmax there. That's why I said it was a bit premature. Basically, to select which output is the largest from them. And then finally, once I'm done with training, I just select the best one, and I end up with, some of these operations, and that's, my subnet or my search network in this case. So this is called differentiable architecture search, and it's basically we're using backpropagation essentially to optimize my architecture itself, right? And so this kind of turns into what's called a bi-level optimization problem because you're optimizing two things. In the normal optimization of training any neural network, you're optimizing the training loss of W, so W is the weights here, with a specific alpha, so with a specific architecture parameter. And then you are also minimizing the validation loss of a neural network with specific parameters, and you're optimizing the architecture parameters here. So, so what happens in practice is, this is very hard to solve exactly, right? Because for each set of architecture parameters, you need to train all of these neural networks separately, right? To actually solve this exactly. But in the paper cited here, DARTS, they do an approximation where they basically alternate training steps. One training step is normal. You use your training data set. You're optimizing your normal neural network parameters. You're trying to find good values for them, and you're keeping the alphas fixed. And then in the second training step, you are training using the validation set, and you are updating the architecture parameters themselves. So you're updating those alphas to see which of the candidate operations are best. So you're updating, the weights that you assign to each of those operations. And so someone sitting there is probably asking, how can we use the validation set in training? This is cheating, right? And the answer is, actually, it's not quite cheating because when we're using the validation set, we're only updating the architecture parameters. And we are allowed to use the validation set to set, hyperparameters of our neural network or topologies. So when we do the normal sample-based NAS, when we evaluate the neural network, we also use the validation set typically. And so this is kind of the reason for also choosing it here. So we optimize these architecture parameters during training, and then finally we keep operations with the largest alpha. So do people have questions about differentiable architecture search? Did the main idea kind of land? Yeah, okay. So basically it's a gradient-based optimization method for architecture parameters instead of being sample-based, which is what we've seen so far. So this actually runs in like 4 hours or something, depending on the data set, but it runs really fast. And usually you don't need to train this for a lot of epochs to get to reasonable architecture parameters. Although I will kind of give some caveats here, is that people have found a lot of problems with this, both empirically and fundamentally, especially on this approximation where they kind of just alternate the training. And so this is a very active area of research where people are trying to figure out how to actually do this bi-level optimization. Okay, back to why we're talking about this. So now we talked a bit about the scalability of NAS. And mainly what that means for us is how can we make that NAS problem more tractable? How can we make it run a bit faster so that we can actually do it on our computers? Now let's talk about the other aspect of efficiency, which is arguably quite important and interesting as well, which is hardware-aware NAS. I have like 3 or 4 slides here, so we're almost there. But this is the case where we want to optimize the neural network, not just to get the best accuracy, but also to have it run well on mobile devices, for example. So if I want to run a neural network on my phone. And people have started by, they were motivated by running this on mobile devices first, but now people do this for all devices because you need a lot of efficiency in your neural networks. It's even for high-end GPUs, you still need to make your neural networks more efficient, and so this is relevant not just for mobile devices but for all devices now. And so what the picture looks like here is only slightly modified from before. So you still have a controller or some search algorithm that proposes your next neural network, and then you train it, you get accuracy, and you provide a reward back. And so this is our regular loop. Now instead of just training it, we're also running this neural network on a mobile phone. We're measuring its latency, and then we formulate this multi-objective reward, which has both accuracy and latency in it. So that's basically it. So we add this extra step of running the neural network on the device that we care about. We evaluate how fast it is on that device, and we use that to provide feedback for the search algorithm, right? And usually we use that latency in one of 2 ways. A very common way is to have it as a hard constraint. So we run the neural network on the phone. It doesn't run under 5 milliseconds. Okay, you throw it away. You don't even train it. So this is a hard constraint. And in other cases, people use soft constraints, where we basically just have a weighted sum of both our objectives. So this kind of goes into the topic of multi-objective optimization in general and how we can combine different objectives. There are usually more hyperparameters introduced here for your search, or your search parameters, let's call them. So basically you have to decide exactly how to combine those 2 weights. Some people multiply accuracy and latency together. Some people add them with a specific weight that they hand tune. But so the first one is usually a bit simpler. And so Harish already kind of mentioned a good point, which is, can we just use number of parameters instead of measuring this on a phone? And we can. And what I'm showing here is not number of parameters, but flops. So the number of operations in the neural network. I can use this as a proxy for this latency. Instead of having a mobile phone and measuring on it every time, and it takes time, I need to convert the model, and I do various things to actually run it on the phone. I can just use flops as an accuracy, and I can compute that in no time, basically. But what we found, and this is again part of the work we did at Samsung, is flops is not a very good indication of measured latency typically for models in a search space. So we took here, I think, 16,000 models in a small search space, and we measured all of the runtime on a specific phone, and we measured, we counted the number of flops, and when we plotted, flops versus runtime, you see here there are a bunch of models that have 100 megaflops, but they have vastly different runtimes, right? And you see this true for all of the other runtimes as well. And so this wasn't a really good proxy for how fast this model runs on a phone. Yeah. So the question is why it's actually not that well correlated, and is it because we're not taking the hardware into account when computing these flops? We're not taking factorization. We're actually not taking anything into account, right? So you're right. So these models may be memory bound. It may be the runtime may be completely unrelated to flops, right? Or some of the layers in this model could be memory bound. So in this case, no matter what the number of flops are, it doesn't really matter. Maybe in that case, parameters would actually be a better proxy. And so, so basically, this doesn't encapsulate any effect of running on actual hardware, and every hardware is different as well. I can run a neural network on, a phone, and it will be memory bound. I can run the same one on a, on a desktop GPU or CPU, and it will be compute bound, something like that, right? And so, and even before going on to the next way of doing this, why do we even want to estimate latency? Why don't we actually run it on the actual device? There are many reasons for that. One of them is it complicates your system. And it doesn't allow you to scale your system very easily. So in the case of sample-based NAS especially, you want to try a bunch of things in parallel. You usually want to run a number of GPUs in parallel, maybe not 800, but maybe 8 or 16. So in this case, you would need 16 phones standing by to also measure the latency of these models. And that can be just complicated, expensive, and not scalable. And so back to estimation. So another way of estimating, runtime is, you have a neural network. You measure the latency of each layer separately, right? So in this case, we have 3 layers. I measure, 3 milliseconds for the first layer, 5 for the second layer, and 2 for the last layer. And then I do that for all of the candidate operations because now, it's broken down into layers. And then I just add those up. And so we tried this as well. And so in this case, the predicted latency from this layer-wise model, from just adding the latency of all of the layers, was better than flops as a proxy for latency, but it wasn't perfect. What we actually want to shoot for is this perfect, y equal x line, where the measured latency would be exactly like the predicted latency. And so what we ended up doing actually was we used, again, another neural network, in this case, a graph neural network, to encapsulate the a prediction methodology for this latency. So we trained the graph neural network to take in the topology of a neural network and to predict the latency at the output. And so again, this was supervised learning. We trained it with a bunch of samples, and then we used it to predict the rest of the samples, and it worked quite well. And here, I think we used kind of 100 or 150 samples for training out of about 16,000 samples. So it was a very small fraction of the entire search space that we used for this. So this is again an active area of research and quite important because this is how you would actually faithfully customize a model to a specific hardware target. And so we found that these prediction-based methods again worked really well. Okay, and this is the final thing that we'll cover here, but a very interesting approach again, which is also something we worked on at Samsung actually, is so far we've been just searching for a neural network and optimizing its accuracy, or searching for a neural network on a specific device and optimizing both its accuracy and latency. But what if you also add hardware into that equation, right? So what we did there is that we are not just searching for a neural network, but we're also searching for a hardware architecture. So this is, we're co-designing both the neural network model architecture and the hardware architecture parameters together. So and we actually used reinforcement learning for this because this is quite early back. And what we did there, we proposed our RNN controller would propose, the different operations to use. So 3 by 3, 1 by 1 pooling, choosing, one operation out of a set of candidate operations. And then the rest of it would choose, exactly the level of parallelism in your processor, or the buffer depth, the size of the buffer on chip, or something like the memory interface width. How wide is that width to your external memory? So we're co-optimizing both the hardware and the neural network parameters in tandem. And obviously, once we do this, we need to fabricate a new chip to suit that specific model. But there are actually, reconfigurable chips. There are FPGAs, for example, which was the topic of this paper, where we can customize an accelerator on an FPGA for a specific neural network. And so I thought that would be kind of interesting to mention as kind of an extension of this hardware-aware neural architecture search is, hardware architecture search co-designed with a neural network as well. And here's kind of a sample of the results, and I'll just highlight this one in green where, we managed to improve both accuracy and performance per area. So performance per area or performance per watt is usually how people kind of quantify how well or how efficient something is on a specific hardware. And we were able to kind of get both a 1.3% accuracy improvement and a 41% kind of efficiency improvement in this case, even though we actually customized the hardware in a very naive and simple way. Like I said, just buffer depth and things like that. So I mean, it increases your search space size, so it makes the search problem harder. So I guess there is a trade-off there. With the same number of samples, you probably can't get to as good an accuracy. Yeah, that makes sense. So yeah, so this is all I had. And by the end of kind of creating these slides, I found that we jumped to so many topics. So I thought I'd have a quick recap of the day. We started by talking about neural architecture search, and the classical algorithms to use there are RL and evolutionary search. And these are sample-based methods where we try a neural network and then we intelligently provide feedback to the searching algorithms to try a better neural network. We then went on to search efficiency, and we talked about parameter sharing, training proxies, and efficient search algorithms there, including differentiable architecture search. Then we talked about hardware-aware neural architecture search, where we're also incorporating an objective of optimizing the latency on a specific device. And we talked about how to predict that latency on devices using different models like flops, layer-wise, or predictor-based. And finally, we touched upon co-designing both the hardware and the deep neural network together. So this is the further reading, and yeah, and AutoML is one of those research areas where there is actually a web page for all of the papers that was published in this topic. There's a group in Germany that curates this list. So if you're really interested, you can click on this link and you can find I don't know, tens of thousands of papers actually. And that's all I had. So thank you.